Vibration analysis. Troubleshooting bearings. A practical guide with real-world examples. Ever wondered what a bearing sounds like when it's on the verge of failure? Or how a perfectly healthy bearing hums along? In this video, we're diving into the world of bearings. Not just by looking at them, but by listening. Bearings can tell you a story if you know what to listen for. Today, you'll hear the difference between smooth, reliable performance and the telltale signs of wear and damage. Get ready to tune your ears to the language of machinery and discover how these sounds reveal the hidden health of your equipment. Bearings play a vital role in countless machines, from the simplest motors to complex industrial equipment. They're designed to reduce friction between moving parts, supporting smooth, efficient operation and protecting critical components from wear and tear. Over time, bearings inevitably begin to wear down, whether through normal usage or due to various external factors that can accelerate their decay. Common culprits include issues like over or under lubrication, which can lead to either excessive friction or a lack of protection between moving parts. Poor mounting during installation can also introduce misalignment, adding unnecessary stress to the bearing and surrounding components. Additionally, exposure to sanitation chemicals, water, and contaminants can degrade bearing materials and cause corrosion, especially in environments where cleanliness is critical. Understanding these factors and identifying their early signs allows us to address where before it turns into a costly failure. This is where vibration analysis comes into play. As bearings start to wear, they begin to produce distinct vibrations and characteristic sounds that reveal the type of decay taking place. Through vibration analysis, we can identify these early warning signs and diagnose the specific wear patterns involved. For instance, a grinding sound may indicate rough or worn surfaces within the bearing, often due to lack of lubrication. Squealing could suggest misalignment or over-lubrication, while a rattling noise might point to looseness or insufficient mounting. By capturing and analyzing these signals, we can take proactive steps to address issues before they lead to costly breakdowns. Before we dive into identifying wear-related sounds, let's establish what a healthy, properly functioning bearing should sound like. A normal bearing operates quietly, producing a consistent, low-level hum or a smooth whirring sound. There should be no intermittent noises, clicks, or irregularities in the tone. This smooth sound indicates that the bearing surfaces are in good condition, with optimal lubrication allowing components to move with minimal friction. In a well-maintained bearing, this hum is steady without any high-pitched or metallic sounds. Knowing this baseline sound is crucial because any deviation from it can serve as an early warning of potential issues. The frequency diagram of a healthy bearing shows a characteristic dominate peak around 50 Hz. The peak's narrow shape and low amplitude indicates smooth, low vibration characteristic of a healthy bearing. Harmonics are multiples of the fundamental frequency, also known as dominate peak, often appearing at regular intervals in well-functioning machinery sounds. In this example, we are looking at a severely worn bearing. The harmonics are at 100 Hz, 150 Hz, 200 Hz, and 250 Hz. In comparison to a healthy bearing, the peaks of the harmonics are much larger, especially at 100 Hz and 200 Hz. Interpretation of the severely worn bearings. The increase in harmonics content indicates an increase in irregularities and noise in the system, which is typically of a sever fault. The machinery is no longer producing a clean sound and is instead generating multiple resonances and disturbances. The higher harmonics, 100 Hz and 200 Hz, dominate the spectrum, signaling instability and vibrational noise that's characteristic of serious mechanical issues. Vibration waveform for healthy bearing displays a low amplitude, steady oscillation with minimal noise, indicative of smooth operation with only minor, random fluctuations. When diagnosing bearing health, one essential test to consider is cross-correlation in time. This method analyzes changes in amplitude, the maximum displacement of the wave. Phase where the wave starts at time equals 0. If the wave starts at time equals 0, then the wave is in phase. If does not, it is out of phase. And frequency, which is the number of waves per unit time, to detect early signs of wear. Subtle shifts in amplitude and phase can point to issues like misalignment or imbalance, indicating that a bearing may be degrading. Changes in frequency components might reveal early signs of spalling or cracks forming on the bearing surfaces. By monitoring these patterns over time, we can catch potential failures early, taking preventative action before they lead to costly breakdowns. Now, let's compare the waveform and frequency charts of a healthy bearing versus the same bearing over time. This is the sound and visual image of a healthy bearing. And this is the sound and image of the same bearing over time. In the healthy bearing, the waveform top chart is relatively smooth, showing consistent oscillations with minimal irregularities. While the waveform in the mildly worn bearing, the waveform appears to have more variability, which could indicate small impacts or increased roughness typical of mild wear. Next, we will perform envelope analysis, which is widely used in condition monitoring and predictive maintenance, as it helps to detect potential failures before they become critical. Envelope analysis is a signal processing technique used to detect and isolate impact or modulation patterns in a signal, especially useful in identifying early-stage faults in rotating machinery like bearings. Envelope analysis captures the amplitude variations, envelope, of high-frequency vibrations caused by impacts, cracks, or other localized faults. This technique enhances fault detection in situations where these impact signals are masked by other components. Now that we've reviewed some basic terminology, we're going to look at some real-world examples. When you spend enough time around equipment, you start to notice both the subtle and obvious changes in sound that signal something might be off. One day, after wrapping up a course on value stream mapping, I was passing by a liquid sugar transfer pump when I picked up on an unusual sound. It stood out immediately. So, I took out my phone, recorded the sound, and later converted it to an MP4 file to analyze with ChatGPT Sound Analyzer. The ChatGPT Sound Analyzer is an invaluable tool for acoustic analysis, capable of running various sound tests to pinpoint issues. From frequency and waveform analysis to detailed spectral examination, it can provide insights into what those small but telling changes in sound really mean. With tools like this, early diagnostics become easier, giving us a clearer path to addressing problems before they escalate. Another important test is the vibration signature, which analyzes the presence of low-frequency vibrations, which could indicate bearing wear, cavitation, or imbalance. A test that simulates thermal imaging is the thermal profile over time. In a healthy bearing, we expect to see a relatively uniform thermal map with minimal heat gradient. As a fault develops, the localized hot spots begin to develop where mechanical friction or where it generates excessive heat. Once the bearings become severely worn, the heat in these regions increases due to friction and damage. By performing a frequency spectrum analysis of the noise coming from the liquid sugar transfer pump, the dominate peak was recorded to be around 50 Hz. The potential issues identified from the frequency spectrum slight spread around 2000 Hz is bearing imbalance, misalignment, or bearing not rotating evenly, resulting in increased vibration. The waveform analysis performed showed significant variation in amplitude over time. This indicates looseness, instability, or uneven wear in the bearing. The visible spikes or impulses in the waveform indicates impact damage, pitting, or scraping inside the bearing housing. Potential issues indicated by the waveform. Potential issues: looseness or wear. The irregularities in the amplitude over time suggest that the bearing might have looseness or uneven wear. This is typical of bearings with surface degradation or improper lubrication. Possible damage: pitting/spalling. The spikes visible in the waveform could indicate impacts from damaged surfaces inside the bearing, where material has broken off. The liquid sugar transfer pump plays a crucial role in food production, making its performance essential. Detecting issues before a catastrophic failure helped prevent unplanned downtime. Upon inspection, the maintenance team discovered that the pump shaft was misaligned, leading to uneven bearing wear. This caused spalling and heat buildup, which if left unchecked, would have resulted in complete failure. Real-world example: HVAC ventilator issue. During a routine Gemba walk, I heard the following noise. The sound depicted is rattling with resonance. On a thermal profile of the ventilator, we'd expect to see localized heating due to uneven distribution of forces, typically causing hot spots near the unbalanced areas. In examining the waveform of the ventilator belt sound, a few key observations stand out. Firstly, we notice that the amplitude gradually increases at the beginning, stabilizing around the 5-second mark. This likely indicates that the system is ramping up or reaching a steady operational speed after startup. After this initial ramp-up, there are noticeable fluctuations in amplitude. These irregular spikes suggest potential issues with the belt, such as slippage, misalignment, or looseness. These conditions could be causing inconsistent tension, leading to variations in the sound amplitude. Additionally, we see a high level of random noise throughout the waveform, particularly in the latter part. This could indicate mechanical wear, such as fraying or damage on the belt, which can introduce irregularities in the sound profile. Around the 10 to 20-second mark, there are more intense fluctuations, which may be a sign of resonance. This occurs when certain frequencies are amplified, potentially due to components vibrating in sync, often because of imbalances or looseness. Overall, the waveform lacks a clear periodic pattern, which we would normally expect in smooth operation. The irregular spikes and disturbances suggest that the belt or related components may need inspection. Possible issues include belt slippage, misalignment, imbalance, or mechanical wear. To confirm these findings, further diagnostic tests, like vibration analysis or a visual inspection of the belt and pulleys, were performed. Each failure type has its own characteristic signature exhibited at a particular wavelength, much like a fingerprint. If the noise coming from the HVAC ventilator is due to fan imbalance or misalignment, then we expect to hear a low-frequency, periodic vibration or clanking sound. The frequency range will show up in the 20 Hz to 100 Hz range. The waveform will show a low-frequency periodic sine wave with some irregular spikes. If the suspect noise coming from the HVAC ventilator is due to worn bearings, then we expect to hear a mid-frequency, grinding or rubbing noise with periodic clanks if severely worn. The frequency range will show up in the 200 Hz to 1000 Hz range. The waveform will show a mid-frequency grinding sound, possibly with periodic spikes. Loose components or panels coming from the HVAC ventilator will sound like rattling or intermittent clanking sounds, typically higher frequency, depending on how looseness of the component. The frequency range will show up in the 500 Hz to 2000 Hz range. The waveform will exhibit higher frequency, rattling with irregular spikes due to impacts. Motor noise or vibration coming from the HVAC ventilator will sound like low to mid-frequency hum or whine from the motor, potentially with vibrations if bearings or mounts are loose. The frequency range will show up in the 50 Hz to 500 Hz range. The waveform will exhibit a steady to low to mid-frequency hum with potential vibrations. If the HVAC ventilator has an airflow obstruction, the noise will be a high-frequency whistling or whooshing sounds due to turbulent airflow. The frequency range will show up in the 1000 Hz to 5000 Hz range. The waveform will exhibit high-frequency continuous waveform representing the whistle or airflow noise. Due to the many variables that could contribute to the sound, I had the sound generator analyzer isolate the soundbite into different frequency ranges. In the low-frequency range, 0 to 100 Hz, common in rotating mechanical systems. Significant energy in this range may indicate misalignment or imbalance, characteristic with a deep, rhythmic hum or vibration. We see some low-frequency energy here, potential, imbalance, or misalignment. In the mid-frequency range, 100 to 1000 Hz, significant energy in the mid-range, indicates bearing wear or belt slippage. Bearing in poor condition often produce repetitive tonal noises in this range, characteristic of a constant whirring or scraping noises. Inspecting the bearings or belt tension would be important. As there is a lot of energy in the mid-region, noticeable peaks. The sound is very likely generated from bearing wear or belt slippage. In the high-frequency range, 1000 to 5000 Hz, the presence of higher frequencies suggests friction or squeaking noises, often caused by worn parts or insufficient lubrication. We see a lot of peaks here, which is an indicator of friction or squeaking. Based on our analysis, the maintenance team inspected the HVAC ventilator and confirmed that the belt was indeed slipping, just as the analysis had indicated. The issue was traced to an incorrectly sized belt that was too thin to fit securely. To prevent this from happening again, we posted clear signage indicating the correct belt size for future replacements. By paying attention to abnormal sounds in our equipment, we were able to identify and resolve this issue early, avoiding a potentially costly breakdown. In this video, we explored real-world examples, breaking down key characteristics of waveforms and frequency charts, such as amplitude, phase, and cycles. We also discussed practical tests to perform, using the sound effect generator in ChatGPT to bring these concepts to life. By understanding these acoustic analysis fundamentals, we're better equipped to detect early signs of equipment issues, prevent costly breakdowns, and maintain a more reliable operation. Remember, sometimes all it takes is listening closely to spot potential problems. Thank you for watching, and I hope you found these insights useful. See you in the next video. If you like this video, please like, share, and subscribe.